Okay, welcome to lecture here. We're going to continue on in chapter 5, I think it is. Okay, so we've been talking about here in chapter 5. We talked about moles and grams and Avogadro's number and molar mass and also atomic mass as well. So we talked about how you can basically solve for the atomic mass, which is what we see on the periodic table underneath the symbols. And as we talked about, those are really what are referred to as usually as average atomic masses, although most people don't usually call it average atomic masses. But what that really means is, as we talked about last time, that those numbers that we see on the bottom of the symbol are the atomic mass of all the naturally occurring isotopes for a particular element. So the way that we could calculate the atomic mass is we take the percentage of each of those isotopes, and that is sometimes what is referred to as the percent abundance or relative abundance of each of those isotopes. And we multiply the percentage of the isotope by the atomic mass of the individual isotope. Then we add it to the second isotope's percentage times the atomic mass of the second isotope. If we happen to have three isotopes, you sort of continue that path of percentage times atomic mass. You add them all together, and that's essentially how we do come up with those numbers that we do see on the periodic table. So as we talked about last time, in reality, if you were to, for example, carbon, if you were to grab out an atom of carbon, you really wouldn't find one that has a mass of 12.01 like we do see on the periodic table. Again, they will either be the mass of carbon 12 isotope, which is 12, or the mass of the carbon 13 isotope, which is 13 and some change going on there. So in addition, we talked about Avogadro's number, which is 1 mole of anything is 6.022 times 10 to the 23. And when we talk about Avogadro's number, the units can change. So a lot of times we use it as units of atoms, sometimes units of molecules, could be particles, but it's always 1 mole of something. And we really use Avogadro's number as a conversion factor to go from units of atoms, molecules, particles into moles and vice versa. And as we talked about last time, you don't want to use Avogadro's number in every calculation that you do. You just want to use it in the appropriate calculation. And that would mean that you have a number that's either given to you in atoms, molecules, or particles, or you're asked to find something that's in atoms, molecules, or particles. Otherwise, you really shouldn't use Avogadro's number. Sort of the conversion that we use a lot is the grams to moles or moles to grams. And to do that, our conversion factor is really the molar mass that we get from the periodic table. And as we talked about last time, essentially the molar mass, which here has units of grams per mole. So when we say the molar mass of something, it's how many grams there are per 1 mole. And the numbers goes with the grams part, and always 1 mole when you do the molar mass. But numerically speaking, the molar mass of a element or a compound is the same as the atomic mass of those guys in AMU. So when we do pull those numbers off the periodic table underneath the symbol, we typically do use it in those units of grams per mole. We also typically pull it off in terms of 4 significant figures is usually what we use when we either calculate the molar mass of something or need to sort of use the molar mass in a calculation. So again, using a molar mass, we could go from grams to moles, which is a very, very common conversion you need to do in chemistry, or again, going backwards from moles back to grams. The relationship between all those things, as we also talked about, was, if you had, for example, 1 mole of lithium, 1 mole of lithium would have 6.941 grams of lithium, and that 1 mole of lithium would also have 6.022 times 10 to the 23 atoms of lithium. And again, that's sort of the arrangement there for all of those. Then we sort of finished up, or before we actually finished up, we also did some conversions there where we did sort of to moles. And we also saw that we were interested in a couple of problems, not in the entire sort of formula, but for example, we're interested in just the hydrogen part. So we saw that you can use the actual chemical formula as sort of a mole to mole relationship, and the subscripts that we see in the little formula are also known as the moles of each of those atoms. So we can get conversion factors from the actual formula itself. And again, that's sometimes very useful, especially when you're asked, like we were in that problem or two, about just hydrogen rather than, say, the C2H8O, the entire formula. Then we finished up talking about at the very end there the percent composition by mass. And to calculate the percent composition by mass of each of the elements, it usually is done based on the chemical formula. So the first thing you want to do is get the molar mass of the entire formula, and then you want to get the mass of each individual element in that formula, also from the periodic table, and then basically take the mass of the element divided by the mass of the entire compound times 100, and that will give you your percent composition of each of the elements in a particular compound. Any questions on any of that stuff there we talked about last time? Okay, so this is sort of where we left off, and we're going to now talk about empirical formulas and molecular formulas. And I'll go backwards here. I'll steal this to write on. So let's just first talk about sort of the difference between those two types of formulas, so everybody sort of understands. When we talk about the empirical formula, the empirical formula is the simplest whole number ratio of what elements are present. So when we look at something that's sort of the empirical formula, it is just that. It doesn't necessarily tell you 100% of the time exactly how many atoms of each element are present, but it does give you that sort of simple whole number ratio of what elements are present, or atoms of the elements that are present. And that's different than the molecular formula, which actually does give you exactly how many atoms of each element are present. You have exactly how many atoms of each element are present. So for example, if I had a molecular formula of H2O2, that's hydrogen peroxide, that is basically 2 hydrogens to 2 oxygen ratio. That's the same as a 1 hydrogen to 1 oxygen ratio. So the empirical formula for something like that would be HO, again, a 1 hydrogen to 1 oxygen relationship, the simplest whole number that's there. You have something like C2H4. That's like 2 carbons for every 4 hydrogens. That's the same thing as saying 1 carbon for every 2 hydrogens. So the empirical formula for that guy would be CH2. So again, sort of the simplest whole number ratio of what's present is basically what our empirical formula is. Typically when, things are sort of discovered or formulas are trying to be determined, usually the empirical formula is the one that you can do a lot of times experimentally and sort of figure out experimentally what the empirical formula is. Now, sometimes the molecular formula and the empirical formula will be the same. So for example, if you had water is basically 2 hydrogens for every 1 oxygen. That's essentially as low as you could go in terms of a whole number ratio. So H2O would be both the empirical formula and the molecular formula. So again, it is possible that they will be the same. In a case like that, water would be the same. It is a version of the molecular formula, so it will have it technically would have sort of a different name based on the relationship there, but it really is sort of based off of the molecular formula. So they probably would have similar type properties if that's more what you're asking. They technically would not be the same compound, if you will, in that sense, because they, one's one carbon and two hydrogens, two carbons and four hydrogens, but they're basically two sort of formulas that are related to each other, essentially. When we talk about ionic compounds always are empirical formulas. So if you remember ionic compounds, when we put them together, the goal here is to put them together in the simplest way that will get us no charge. So that's why we go Na2O. So whenever you write something that's an ionic compound, always an empirical formula. Again, that's why when we talked about, or we will talk about, you technically could write this here, 4O2. That technically is balanced. You got +4 here, you got -4 here. It's technically 0 in terms of the charge. But that's why in an ionic compound, we always go with the simplest ratio, because you can reduce these down to N2O. And so when we do anything that's sort of an ionic compound, the idea behind, when you probably have learned positive, negative, 0, the simplest way to get yourself to 0. And that's because all ionic compounds basically are empirical formulas, because they should come together in the simplest whole number ratio that will give you a charge of 0. Question on the difference there between empirical and molecular formula. So if you have a molecular formula given to you and you're asked for the empirical formula, you essentially can just reduce it down by the simplest whole numbers. And that means you need to divide all of the subscripts by a common number and still end up with whole numbers for all the subscripts. So that's one way that you could kind of calculate the empirical formula. We're going to now talk about really the more common way, I guess, to calculate an empirical formula. When we go to calculate the empirical formula, there's several sort of steps to follow. And the first, they're kind of outlined over here on the left here. So a lot of times when we kind of deal with empirical formulas or trying to calculate empirical formulas, sometimes they'll give us that percent composition by mass, like we just calculated on that previous example at the end last time. And when you're given a percentage and you want to kind of turn a percentage into a number, a lot of times it's good to assume that you got 100 grams. So if you have 100 grams of something and it's 50% carbon, that means you would have 50 grams of carbon. Makes the number pretty easy. They remain the same numbers. You just convert them into grams. So if you are given things in percentages, you want to convert them to grams. Then you want to convert the grams into moles. So you want to convert the grams into moles using the molar mass from the periodic table. So grams to moles here. And at this point, what you will have is the moles of every element that's present. And then what you want to do is look at all the moles that you just calculated for each element. So for example, let's say we had moles of A was 2, and say moles of B was 4. What we would want to do is look at the moles of each of the elements that are present, and we want to divide everybody by the smallest number of moles. So in this case, it would be 2 in my example. So I would divide 2 by 2, that gives me 1. I would divide 4 by 2, that gives me 2. And if you divide everybody by the smallest number of moles, what that will give you is the empirical formula if everything hits a whole number. So in this case, it did. And this would mean that my empirical formula, my made up one here, would be AB2. And again, if you get whole numbers here, you're pretty much done. That will be your empirical formula. Now, let's just say, for example, that I had moles of A was 2 still, but my moles of B was 5. Now, when I divide by 2, I get 1. I'm going to go without the calculator here and go for 2.5 and hope for the best. I got 2.5 here for B, and that would mean my empirical formula would be A, B, 2.5. Problem is, you cannot have like a half an atom, so all these guys do need to be whole numbers. So this guy obviously is a whole number. This one is not a whole number. When you get a number like that, that it's like ends in 0.5, 0.33, 0.25, 0.75, whatever it may be. Those are too far to round to the nearest whole number. So what you need to do is figure out a number that you can multiply the entire formula by to get to a whole number. And in this case, you could just do the old trial by error. If you take 2.5 times 1, you got 2.5. Take 2.5 times 2, you get 5. And that obviously is a whole number. And what you would want to do then is take this guy and multiply everybody by 2, not just the 2.5. And if you do that, that would give you something like A2, B5. And that would be your correct empirical formula in this case. So when you're doing the dividing by the smallest number of moles, in order for you to round, I would say in a textbook problem, in order for you to round, it does need to be really close. So, you know, like 0.9, 0.99, maybe just a little bit over the number, 0.01, 0.05, something like that. Typically, if you get anything like 0.25, 0.33, 0.5, those are too far away to round to the whole number. You need to do something like what I just did there to try to find a number that you can multiply everybody by to get everybody into a whole number. And again, if you do all that, that should give you your proper empirical formula. Question on that there. Okay. So let's actually take a look at one here together and kind of go through the steps just to make sure everybody will do good. So we'll take a look at this one here. And in this particular case, we are looking for the empirical formula. We're looking for the empirical formula of a compound that is made up of 24.75% potassium, 34.77% manganese, and 40.51% oxygen. When you're given percentages such as these, it's always a good idea to just kind of quickly look at them and make sure that you do have something near 100%. So it should add up to 100%, may add up to a little bit more than 100, maybe just a little under 100, like 99 point something, but it should definitely be in the 100% sort of range. If you add up all your percentages and it's not in the 100% range, then you're probably missing something. You're missing an element or something like that. There's probably other information to help you figure that out. But in this particular case, if we just do a quick kind of look over, we do have pretty much 100%. So in this case, we do want to convert our percentages into grams. So we could assume 100 grams here. And when I assume 100 grams, what that means is I will have 24.75 grams of potassium. I will have 34.77 grams of Mn and 40.51 grams of oxygen. So again, that's basically this step right about there. The next thing that we want to do is we want to take each of those, use the molar mass from the periodic table, and we want to convert each of these into moles. So going to the periodic table for potassium, that is 3910. Going to the periodic table there for Mn, looks like maybe 5494. And lastly, going to the periodic table there for oxygen, looks like we got a 16 grams per mole working. So again, once we get everybody into grams, we want to get everybody into moles. So if we do that sort of calculation there, 2475 divided by 3910, we get something like 0.6330, we'll call it. 0.6330 moles of potassium. We take 3477 divided by 5494, gives us 0.6329 moles of Mn. And lastly, if we take 40.51 divided by 16, and actually hit in all the numbers would probably be helpful there. 40.51 divided by 16. There we go. 2.532 in terms of that. Of oxygen. Any questions up until this point? Okay. So now that we have each of the elements converted, by the way, sometimes people, when they do these type of problems, they all of a sudden go, well, that's oxygen. It's kind of by itself, so it should be O2. It should not be here. You don't know how many oxygens you have, so don't try to use like the molecular version of it or anything like that. That's the point of what we're doing here, is to try to figure out, obviously, how many moles of each of those guys we have. At this point, what we want to do is look at each of the moles that we got going here, and we want to find the one that is the smallest. So I'm just going to rewrite them on the next page here. So we had 0.633 moles of potassium. We had 0.6329 moles of Mn, and lastly 2.532 moles of oxygen. So at this point, we can see pretty close. They're about the same, but it does look like slightly the Mn there is the smallest out of all those. So we're going to divide everybody by 0.6329. And if we do that, in terms of what we get about 1 here, we get about a 1 here. And if we divide that last guy there, we get approximately a 4. Now, in this case, since we divided by the smallest number of moles, which is what you always do, we hit pretty much all whole numbers. That means that will be our empirical formula. So it should be KMnO4 would be our empirical formula, which is, in this case, potassium permanganate is actually what it is. Question on any of those sort of steps there? So it really is sort of the same steps when you have to calculate the empirical formula, get it into grams, and usually if it's not in grams, it's in percentage. So assume 100 grams, grams to moles, divide by the smallest. If you hit all whole numbers, you're good. If you don't, obviously you need to kind of clear it. Any question on any of those steps? Okay, so this is one type of empirical formula type problem. There is another type of empirical formula problem, which is common as well, and it involves a particular type of reaction, which is a combustion reaction. And in a combustion reaction, we use sort of the products that typically occur in a combustion reaction to help us figure out basically the empirical formula. So this would be sort of like an experimental type of way that you sometimes can figure out a empirical formula. And if you're not familiar with a combustion reaction, let me familiarize you with it here. Usually in this type of combustion reaction involves an organic compound, and that's usually something that contains carbon, hydrogen, and oxygen. You react that with O2, and when you do this type of combustion reaction, you pretty much always get 2 products, which are always carbon dioxide and water. So in this sort of reaction, works really well for organic type compounds, which again are pretty much carbons, hydrogens, and oxygens, always producing CO2 and water. And the purpose, or what we do here in this sort of experiment, is, as we'll kind of see a better picture in just a second, but essentially what happens when you do this type of sort of analysis is we have places where we can collect CO2 and we can collect the H2O. So we're able to really sort of collect how much CO2 comes out and how much H2O comes out. And the reason that's important is since the organic guy pretty much contains carbon, hydrogen, and oxygen, the CO2, all the carbon that ends up in that CO2 had to come from my organic guy. So we're able to use how much CO2 we got to figure out how much carbon was in our original compound. Same thing here, all the hydrogen that will end up in water had to come from my organic guy. So we could use the amount of water that we actually collect to figure out how much hydrogen was in the original sample. So the question is, can I use those 2 to figure out the oxygen? And the answer is we cannot use the mass of the CO2 and the H2O to figure out how much oxygen was on our original guy. And that is because to do this reaction, we have to dump in their oxygen. Yeah, so we have to throw in some oxygen. So some of this oxygen that we threw in will end up in these guys. So we can't really use the oxygen part of those things, but that's okay because we could use the CO2 to figure out the carbon part. So we can figure out the mass of the carbon that was in the original substance. We could also use the H2O to figure out the mass of the hydrogen that was in the original substance. So if we take both of those things and add them together, and then take the mass of the original substance and subtract it, the only difference then would be the mass of the oxygen that was there presently. So we're going to use the CO2 in the water basically to figure out how much hydrogen and carbon was in our original sample. Then we're going to do the difference between our original sample's mass and those two masses, and that's going to allow us to figure out how much oxygen was there originally. Remember, conservation of mass, right? So if I started with the carbon, hydrogen, and oxygen, the difference here is just going to be how much oxygen was originally there in that particular case. This is going to require us to do some calculations like we did the other day, where we're not interested in the CO2 altogether. We're just interested in the carbon part of it. And we're not interested in the H2O altogether there. We're just interested in the hydrogen part. So let's take a look and kind of go through one here again together so you can kind of see how it all works out, what we're trying to find in this type of calculation. So let's take a look at one. And here's sort of the setup. We have our O2 that we shoot in there to some ethanol. Ethanol basically is made up of carbon, hydrogen, and oxygen. So when this reaction takes place, it's going to produce our CO2 and our water. We have something that will absorb all of the water. We have something that will absorb all the CO2, and we're able to figure out basically the mass of each of those that we collected. So again, as we were just talking about, what we're going to do is use those masses and some calculations to figure out how much carbon was originally there. So that's the first part of the calculation we will probably want to do. We want to figure out how much the mass of the carbon in the original sample. And we do that from the mass of the CO2. So we're going to take the 22 grams of CO2. And what's going to allow us to go from CO2 to just carbon is that relationship that we talked about the other day. I could use the actual formula for CO2. And from the formula, I see that for every 1 mole of CO2, I get 1 mole of carbon. I could also do it for oxygen, but we're not really interested in oxygen in this case. Since this is a mole-to-mole relationship, we do need to convert our CO2 into moles. So that's why we're going to convert this into moles here. So to do that, we would go to the periodic table. You would have 1 carbon at 1201 plus 16 and 16, which is 32. And if you add all that together from the periodic table for CO2, it is 4401 grams per mole of CO2. Now, if I stop right there, I have moles of CO2. You don't necessarily need to get an answer here, but I'll throw one up here just because. So if you kind of throw an answer in here, you got something like 0.49989. I'll take it to a few digits, moles of CO2. Again, here, we're not interested in the moles of CO2. We want just the carbon part of it. So that is why we're going to use this relationship here that comes from the actual formula. And just like we did the other day, we're going to get rid of the CO2, which in this case is 1 mole of CO2, gives us 1 mole of just the carbon in this case. That is going to get rid of the CO2, get us just to the carbon. And I believe it should still be the same number, 49989 moles of carbon. Lastly, we're really looking for how many grams of carbon was in the original sample. So we're going to use the molar mass at this point of just carbon since we converted to carbon. So that's going to be 12.01 grams per mole of carbon. Moles are going to cancel. And finally here, we will end up with, we'll call it 6 grams of carbon. So what this number represents is all of that carbon. The only source of carbon in this entire reaction came from ethanol. And 6 grams of it had to come from that ethanol. So what we know is right now, ethanol is 6 grams of it was carbon. Any questions on that part of the calculation? We're now going to do the exact same type of calculation for water to figure out how much hydrogen was originally in there. So we're going to do the mass of hydrogen in the original sample. And again, the hydrogen is going to end up in the water. So we collected 13.5 grams of water. We again could use the formula as a conversion factor to go from moles of the whole thing to moles of the hydrogen. So in this case, it's actually 2 moles of hydrogen for every 1 mole of water. So just like the one above, we need to convert our grams into moles. So again, if you go to the periodic table, 2 hydrogens gives you about 2,016 plus 16 for the oxygen gives you 18.02 grams per mole from the periodic table for water. Again, you don't necessarily need to get a number here, but I'll put it up there. So 13.5 divided by 18.02 gets us something like 0.74917 moles of water. Again, we're not interested in all of the water. We want just the hydrogen part. So we're going to use that relationship that we got from the formula. And we see that for 1 mole of water, we get 2 moles of hydrogen. Again, comes right there from the actual formula. And that's going to get us 1.4983 moles of hydrogen. Again, we do want to figure out the grams. So we're going to take that and convert that into grams. Now that we've converted to just hydrogen, we want to go to the periodic table and molar mass for just the hydrogen, which is 1.008 grams per mole. And it looks like 151 grams of hydrogen. Any question on that part of the calculations so far? Okay, so at this point, we have now figured out how many grams of carbon was in our original sample, because all of the carbon had to come from our original sample of ethanol. We also just figured out how many grams of hydrogen had to come from our original sample. Again, all the hydrogen is going to be provided by the ethanol. So like I said before, we cannot use water or the CO2 to figure out the oxygen because as you can see here, we are adding oxygen by itself. So what we're going to use now is the third number that was given to us, which was, this is the mass of the original sample. So basically the original sample, which contained carbon, hydrogen, and oxygen, had a mass of 11.5. So what we know now is we can use our numbers we just calculated, and we could take 11.5 grams minus 6 grams for the carbon, minus 1.51 grams for the hydrogen. And what that's going to leave us is looks like 3.99 grams, and that is going to be the grams of oxygen that was present in the original in the original substance. Any questions on that? So this is typically how combustion sort of analysis works. Again, the water gives us the hydrogen grams that was there originally. The CO2 gives us the carbon grams there originally. Using those together and the original mass of the substance will give you how much oxygen. Now that you've done all this work here, you're now ready to actually do the empirical formula part of the calculation. So now that we have the grams of all of our elements, we want to convert them into moles. The good news is if you did get an answer like I did here, you actually have two of those numbers. So that is the moles of carbon right there. So I don't need to recalculate it. And right there is the moles of hydrogen. So I don't necessarily have to recalculate that one either. So really the only one I need to calculate is kind of my oxygen here. So let me just copy those over. So we got 0.49989, I guess I could have rounded, 0.49989 moles of carbon. We had 1.4983 moles of hydrogen. And we do want to kind of convert our grams of oxygen, which in this case was about 3.99 grams of oxygen divided by 16 grams per mole from the periodic table. And if we do that, what we got there, 399 divided by 16. We end up with 0.2494, since I'm taking so many digits, moles of oxygen. So we'll add that over here, 0.2494 moles of oxygen. So at this point, we now have all of our elements into moles. We want to divide by the smallest in this case. And in this case, it looks like the smallest is going to be our oxygen. So we're going to divide everybody by the oxygen and see what we come up with. So we're going to divide by 0.2494, everybody by that. And in terms of what we end up with is we got 1 there. We end up with 0.49989 divided by 0.2494. We got about 2 for our top guy. And here got about 6. So we hit whole numbers, which is good. That means that will be our empirical formula. So C2H6O would be our empirical formula on this particular one. Question on any of those steps. So sort of a combustion analysis one is sort of the same deal at the end. You just got to do a little bit more work to get all the grams to start with. Then you get the grams to the moles and do it on there. So just a little bit extra work on this type of one because of the way it was done through this analysis. Question on any of those steps, how to calculate an empirical formula, these couple of ways here. Okay. So is there a specific order? Truth be told, usually if it's carbon, hydrogens, and oxygens, you got those in a formula. Most of the time, carbon and hydrogen kind of comes first, and then everybody else after that, oxygen or somebody at the end. The real answer is a molecular formula basically just kind of tells you what's there, or an empirical formula, or any formula really just tells you what elements are there. There's not necessarily a right way for a compound like this, but traditionally carbon usually kind of goes there first, and then hydrogen and oxygen. The only one where there really would be a specific order would be something that was like an ionic compound, like actually this guy here that we solved for previously. This particular one, which is potassium permanganate, technically speaking, this is ionic, and the potassium is positive, the permanganate is negative. So always with an ionic compound, positive guy, negative guy is sort of the rule. When you get into more molecular compounds, which are nonmetals, you know, not necessarily a particular order, but typically if carbon and hydrogen and organic guys sort of involved, usually carbon, hydrogen, and then the other elements are usually kind of put in there. Other questions on that? By the way, this is, ethanol is basically this here. So just to show you can have sort of another sort of formula for it. It looks something like this. If you draw ethanol, it's ethyl alcohol, the alcohol of alcohol, right? So you could also sometimes write this. Sometimes people write CH3, CH2OH. Same deal, basically. Just another way to sometimes people write a formula. This way that I just wrote here that I'm circling gives you a lot more structure information. So sometimes people call this more of a structural type formula because it has that sort of how things are connected. They do represent the same thing. Is again, this first one that we got really doesn't give you a lot of information about how it's put together. So, formulas can be in different ways that they're written, even for the same sort of substance as well. Other questions? Okay. So now that we've talked about how to calculate an empirical formula, let us talk about how to calculate a molecular formula. So if you need to calculate a molecular formula, you pretty much need three things to calculate a molecular formula. One thing that you need is you need to know the empirical formula. So in some cases, they may actually give you the empirical formula in the actual problem. If they don't, then you need to calculate the empirical formula like we've just been doing. Once you have the empirical formula, you need the molar mass of the empirical formula. So once you get it, you need to go to the periodic table, figure out what the molar mass is. And then the third thing that you need is the apparent molar mass of the actual compound you're dealing with. The good news is that number is usually given to you. So this number here is usually given to you in the problem. So somewhere in the problem, they'll say something like the apparent molar mass of this compound is 500 grams per mole, has an approximate molar mass of 255. So somewhere in the problem, they typically will give you that. So in certain cases, what you're left with is you need to calculate your empirical formula, get the molar mass of the empirical formula. Once you do that, you're going to take the molar mass they gave you in the problem, you're going to divide it by the molar mass of the empirical formula, and in most cases, this will give you pretty close to a whole number. In this case, if it doesn't give you a whole number, it's probably safe to round in this case to the nearest whole number. It should be pretty close in most cases. And what that means is, for example, let's say we had an empirical formula of AB2 was our empirical formula. And let's say we did this and we got a number of 4. What that means is we would take our empirical formula and multiply everybody by 4, and we would get A4B8. And this would then become our molecular formula. Sometimes people will write it when they're doing this, not too often, with parentheses and the 4 on the bottom. Most people will distribute it and kind of write it like that, but technically speaking, not necessarily wrong to write it like I did on the bottom right there. Any questions on that there? All right, so why don't you give one a go here? So we got a sample, contains boron and hydrogen, has an approximate molar mass of 30 grams per mole. What is the molecular formula? I'm going to give you some numbers in case you don't have a periodic table. Boron is 1081. And hydrogen is 1.008. All right, so we're looking for the molecular formula here. So see what you come up with. Okay, so let's take a look here and see how we're doing. So in this particular case, we're looking for the molecular formula. So again, the three things that you essentially do need is the empirical formula. You need the empirical formula's molar mass, and you need the molar mass of the compound. So here they do give us the molar mass of the compound. So we got that. We don't have any sort of empirical formula information. So we do need to basically figure that out. So we're going to figure it out like we normally do. So we're going to take our 6.444 grams of boron using the molar mass of boron from the periodic table, 1081 per mole. Going to give us something like 0.5961 moles of boron. We'll do the same thing for hydrogen here. So that's 1.803, and that's grams of hydrogen. From the periodic table, molar mass of hydrogen, 1.008 grams per mole. Again, that will give us 1789, looks like. Again, at this point, we do want to divide by the smallest number of moles. So in this case, it does look like it is going to be our 0.596. And give us 1 there, and 0.5961 and give us about 3 there. So we did hit whole numbers, which is good. That means that our empirical formula will be BH3. So again, that's our empirical formula. So now that we have our empirical formula, we need the molar mass of it. So the molar mass of BH3 would be our 1081 plus 3 times 1.008. Going to give us about 13.834 grams per mole. Now that we have the molar mass of our empirical formula, we have the molar mass of the compound. We're going to divide those two numbers. So 30 divided by 13.834, going to give us a number. And again, that number is going to be the factor by which we're going to basically multiply that for. So in this case, you do get something like 2.16. As I mentioned, this is the one spot where you can pretty much round to the whole number here. Again, because a lot of times this number that they give you is not the true molar mass, it's the apparent molar mass. So it's not going to be perfect sometimes here. So here you can round to the nearest number, which would be 2. And that means that my molecular formula would be B2H6. Or again, you could write it if you wanted to, something like this. But most people, again, will probably distribute it there. So my molecular formula there, B2H6. Any questions on any of those steps? All right, then let us try another one here then. So next one that you got is we're looking at phosphorus and oxygen. Again, we want the empirical and molecular formula there, and they give us an approximate molar mass in that particular compound. So give that a go when we give you some numbers in case you need. Phosphorus there is 3097, I think. And oxygen is 16. All right. So again, here we're looking for both the empirical and molecular formula. See what you come up with. Okay, so let's see how we're doing. So again, same idea here. We've got some percentages given to us. We do have the apparent molar mass. We're looking for both the empirical and molecular formula. So we can approach it sort of the same way. We'll start with the empirical formula. Since we have percentages, they do add up to about 100% there. We're just going to assume 100 grams, and that means that I would have 4364 grams of phosphorus. I would also have 56.36 grams of oxygen. We're going to convert those guys into moles. So we're going to divide by 3097 here. And divide by 16 here. Going to give us, looks like perhaps 1.409 moles of phosphorus and maybe 3.523 moles of oxygen. At this point, we want to divide by the smallest, always the smallest here. So we're going to divide by the phosphorus in this case. And when we do that, looks like for the phosphorus, we get 1. For the oxygen, about 2.5 looks like what we end up with there. Any questions up to that point? So in this case, if we stopped here, we would have an empirical formula of PO2.5. Again, this is not good because it does have to be a whole number. 0.5 too far to round, so we do need to find a factor to multiply everybody by. And again, 2.5 times 1 is 2.5. 2.5 times 2 is 5. So we would want to multiply everybody by that factor of 2. And again, not just the oxygen, but the phosphorus as well. So that's going to give us P2O5. That is going to be our empirical formula. Any questions up to there? Now that we have the empirical formula, we have the molar mass of the compound that was given to us. We need to get the molar mass of our empirical formula here. So the molar mass of our P2O5 going to be 2 times 3097 plus 5 times 16. And we'll go with 141.9 grams per mole. So now we got the empirical formula's molar mass. We have the molar mass of the compound. So again, to find our molecular formula, we're going to divide those two. So our bigger number here up on top, our smaller number there on the bottom. And looks like we will end up with about 2. And again, this 2 is what we will now multiply our empirical formula by, giving us P4O10. Looks like a winner for our molecular formula. Any question on those steps? So this is, yeah, this question?
For the empirical formula,
yeah,
how did you get 2 phosphorus?
I got 2 phosphorus because originally we ended up with, for our empirical formula, when we did the dividing by the smallest, we ended up with this guy here.
Yeah.
And what we were trying to do is basically figure out a number that we can multiply the 2.5 by to get a whole number, and that number is 2.
Okay.
But when we do that, we do have to multiply not just the oxygen by that, but we got to multiply the phosphorus by that because they're basically together. So you got to multiply everybody by that. And so the 2 needs to go not just to the 2.5, but to both of them there. Yeah. And that's how we end up with the P2O5. Yeah.
Okay, thank you.
You're welcome. Other questions? Okay. So this is one approach that you could do, and another sort of common sort of approach that sometimes people will do with these when you're given the percentage and you're given the molar mass of the whole thing is to kind of do a percent composition by mass calculation. where you get the molecular formula first and then work your way backwards. So just to kind of show you how you could kind of do that as well. If you wanted maybe a different approach, we know that we had 43.64% phosphorus by mass and 56.36% oxygen by mass. We know that the molar mass of the compound is about 283.89 grams per mole. We can convert these percentages into a decimal, and if I take 0.4364, which is our percentage of phosphorus, and I times it by the 283.89 grams, that will tell me that out of that 283.89 grams, 43% of it is phosphorus. That's roughly 123.89 grams of phosphorus. You then can use the molar mass of phosphorus and divide by 30.97. And if you do that, you get 4 moles of phosphorus. You could do the same thing for our oxygen, which was 0.5636% oxygen, times it by the molar mass. And what that will give you is how many grams of your compound was made up of oxygen. Gives you about 160.00 grams oxygen, also dividing by the molar mass here of oxygen. Gives me 10 moles of oxygen. Was that oxygen? It was oxygen. That's good. And that would actually be your molecular formula, which would be P4H10. And then you could go, that is 4 phosphorus for every 10 hydrogens. That is the same as reducing it down to 2 phosphorus for every 5 hydrogens, which would give you your empirical formula of that, except that is oxygen. I don't know why I keep writing hydrogen there. Let me actually put the right element there. There we go. Take 2, throw some oxygens in there. There we go. Oxygen, oxygen, 10 oxygens, 5 oxygens. And that would be oxygen. And you can go this way, empirical formula. So this is an alternative sort of approach where you kind of get the molecular formula first, and then just reduce down the molecular formula to the empirical formula. You can do it either way. It should come out the same as long as you do sort of the math correctly. Question on a sort of an alternative approach to this. Okay, so let's try one more, I think, here. You got. So try your vitamin C one there. Carbon, hydrogen, and oxygen. What is the empirical and molecular formula you got going on in that one? Yeah, you can use either one. It's perfectly fine. As obviously you need to show the work for whichever way you kind of do it, you know. So technically you can do it either way, so it'll come out the same. All right, so again, in case you need some numbers, carbon is 12.01. Hydrogen, 1.008. And our oxygen is 16. Okay, so let's take a look, and we'll start the traditional way of doing it. So we have the percentages. If you add them all up, we do got about 100%. So we're just going to convert those into grams. So 40.9 grams of carbon. We're going to divide that by the molar mass there to get it into moles. We're going to take 4.58 grams of hydrogen, also going to divide it by the molar mass to get it into moles. And lastly, 54.5 grams of oxygen, also going to divide it from the periodic table by the molar mass to get our moles. And if we do all that good stuff there, looks like 3.41 moles of carbon for 54 moles of hydrogen and 3.41 moles of oxygen. Looks like in this case, if we take our carbon, our oxygen, same number, and divide by the smallest, going to give us a 1, and I believe here a 1.33. So in this case, we would have CH 1.33. O is our empirical formula. This is not good because it's not a whole number. So again, if you take 1.33 times 1, 1.33, 1.33 times 2, 2.66, 1.33 times 3 equals 3.99, which is close enough to 4. So we want to multiply everybody by that factor of 3 here. And if we do that, we're going to end up with a proper empirical formula of C3H4O3. Any questions on that part so far? So now that we have the empirical formula, we need the molar mass of it to calculate our molecular formula. So 3 times 12.01 plus 4 times 1.008 for our hydrogens, plus 3 times 16 for our oxygens. Going to give us a empirical formula molar mass of about 88.06. So again, we're going to take the number that they gave us, and we're going to divide it by that number we just got there, 88.06. Going to give us a number, again, hopefully pretty close to a whole number. If not, this again is an okay place to usually round. And it does look like we end up with a 2. So remember, the 2 is the factor we want to multiply our empirical formula by. And that will give us a molecular formula of C6H8O6 as our molecular formula. Question on that one there. Now, in case you do want to kind of see it, the other way of doing it, doing molecular formula first, just so you can kind of see it. I will work that out for you real quick, and you can kind of compare which one you like better or not. But again, here what we will do is take the percentage of each of those guys, convert them into a decimal. We're going to multiply it by the molar mass of the compound that was given to us, because that's basically the total grams of all those elements together. So it's basically 40% carbon, so 176.13 gives us 72.037 grams of carbon. We're then going to divide by the molar mass of carbon to give us how many moles will be in our molecular formula in this case. And we get 5.998, which is pretty close to 6 moles of carbon. Then we would do the same thing for our percentage for hydrogen, 0.0458. Either move the decimal 2 places to the left or divide by 100. And we end up with 0.0458 times 176.13 gives us 8.0668 grams of hydrogen. Again, dividing by the molar mass of hydrogen gives us about 8 moles of hydrogen. And lastly, our oxygen was 0.545 basically percent, 54%, 176.13. Tells us that out of that 176 grams, there is roughly 95.99 grams of oxygen, dividing by our molar mass of oxygen, 16 grams per mole. And again, when you do it this way, you get 5.999, which is about 6 moles of oxygen. Again, this gives you your molecular formula first, which would be C6H8O6. And then that's basically a 6 carbon to 8 hydrogen to 6 oxygen relationship. You can divide everybody by 2. Basically, it gives you 3 carbons to 4 hydrogens to 3 oxygens, giving you your empirical formula of C3H4O3. So again, kind of 2 approaches to these problems. As you can see, pretty much with rounding, should get pretty much the same thing. You could do it either way, whichever approach you like. You just need to make sure you show the work, obviously, for either way that you do it. Any questions on how to calculate an empirical formula, molecular formula, any of those things? Okay, so that should wrap chapter 5. I think next week on Thursday, I think we should have a quiz. We're going to have a quiz on the Lewis structure stuff. So what's that, 3 and 4? So we'll do Lewis structures, formal charge, bond polarity, molecular geometry, and molecular polarity and hybridization. It'll be a good warm-up because our second exam is rolling up on us in a couple of weeks or so from now. So that was a lot of stuff in that chapter. So good idea to maybe have a quiz before the exam. So we'll do it kind of like what we did last time, probably next Thursday at the start of lab, we'll take the quiz. And again, it'll be on chapters 3 and 4. So drawing Lewis structures for both covalent and ionic compounds, electronegativity, bond polarity, formal charge, hybridization, geometry, and I think that's all of it. So that type of stuff, all that stuff that kind of goes together that we talked about. Any questions on that there? So we're going to do experiment 7 today. So we'll talk about experiment 7, which is a formal lab, and it involves, now that we've officially talked about it here, it involves basically empirical formulas and stuff like that. So you should be set up good to kind of work on that one as well. So I'll see everybody about 7:15. Make sure you put here if you haven't done so, and we'll talk about experiment 7, I believe.